In this video, we're going to talk about applied force and friction. Now, an applied force is very easy to understand. Draw a box and a little stick figure pushing that box. Well, that stick figure is applying a force, and if I drew it on my picture, it might look like that. Now, this is also sometimes called an external force because something outside of the box is applying a force, so it's external. But we just label this thing with F for a force. Now, you can always label applied forces or external forces with subscripts that are more descriptive. Like maybe you want to say F sub A because it's an applied force, or maybe you want to say F sub U because you're applying that external force. I will always just write F because I think it's a little cleaner. Now, if you're going to draw a free body diagram for this, you would have the weight, which you would write mg, and then a normal force acting up because the floor is holding the box. They are balanced because it's not going up or down. And this force I would draw coming out just like that. Notice that I don't draw the applied force pointing at the dot because that would be incorrect. Now, F for external or applied force is very good and easy to use, but you have to make sure that you recognize that this is not necessarily the same thing as sigma F, or the net force. And that'll make more sense once we've done some problems. So let's do some problems. You lift a 100 Newton rock, which is about 22 pounds, with a force of 150 newtons, or 33 pounds of force. Draw a free body diagram and find the acceleration of the rock. Okay, so I'm going to draw a dot representing the rock, and then I'm going to have the weight acting down, which is mg, and I know that that weight force is equal to, for the rock, 100 newtons. Okay, so that's the weight of the rock. We use pounds often, but newtons are the SI or metric unit of force, while pounds is the British unit of force. Okay, then you lift up with a force of 150 newtons. Well, what's that? That's your applied force. So all you have to do is draw an arrow up for your applied force and label this F. If you want to write F sub A or F sub U, that would also be fine. This is 150 newtons, and it is bigger than my weight force. So when I want to find the acceleration of the rock, I remember that the acceleration is equal to the net force divided by the mass of the object. So all I need to do is find the net force and then find the mass. Let's start with the net force. To find the net force, I notice that there are no x forces, so I don't need to take a look at those. There are only y, or vertical forces. The external or applied force goes up, so I'm going to write sigma F equals F for my applied force up, minus the weight force going down. So I'm using minus because that force goes down. Then I can write the numbers in. 150 newtons minus 100 newtons. So the net force is 50 newtons, and it's positive, which means that the overall net force would point up. And of course, if you're going to draw the net force, never draw the net force on the free body diagram. Just draw it off to the side to help you visualize it. Okay, so if the net force is 50 newtons, how do I find the mass of this rock? Well, it's easy. I just remember that the weight, 100 newtons, is equal to the mass times the acceleration due to gravity. So if I divide both sides by the acceleration due to gravity, I'm going to get the mass. Let me write that. Mass equals 100 newtons divided by the acceleration due to gravity, which to make our lives easier, we use 10 instead of 9.8. So 10 newtons over 100 newtons over 10 meters per second squared. Remember that a newton is a kilogram times a meter per second squared. So those units cancel out. This gives you 10 kilograms. So the mass of the rock is 10 kilograms. And now I can use that here for the mass in my acceleration equation. And 50 newtons over 10 kilograms, now we're going to get the kilograms canceling out. And that'll give me 50 over 10, or 5 meters per second squared. So that is the acceleration. Let's do another problem. You push your friend who weighs 600 newtons, or 135 pounds, with a force of 200 newtons, or 45 pounds of force. Your friend is wearing frictionless rollerblades because they are fancy. Draw a free body diagram, so I'm just going to start saying FBD for short, and then find the acceleration of your friend. Okay, well, your friend has weight, so I'm going to draw the weight force first. And I know that the weight is 600 newtons, which, you know what, before we do anything else, I feel like I'm going to need to find the mass again, since it wants acceleration, and to find acceleration, I do net force over mass. So to find the mass, I would take that 600 newtons and divide by 10 meters a second squared. That's what G is. And so that's going to give me 60 kilograms. Okay, so just so that we have that there. This is like separate. Okay, so I've got the weight force down on my free body diagram. They're on the ground, like if you're on rollerblades and the ground is supporting you, so there's going to be a normal force. And this isn't an elevator or anything. The rollerblader isn't jumping up or falling down, so I know the normal force is balanced by the weight, or balancing the weight. So those two things are equal, and even though I don't need to know this, I might write 600 newtons just in case I needed it later. Okay, so what about this push that you give to your friend? Let's say you're pushing to the right, and you might be tempted to do this, but don't, because that's incorrect. Instead, we draw your push, or your applied force, coming out of the dot to the right, and then we label that F. Now, the force that you're pushing with, 200 newtons, you can write that there if you would like. Okay, so that's the free body diagram. Congratulations. I'm going to get rid of this mass so that we just see the free body diagram. Hopefully that's what you drew. And you don't have to include these numbers. The numbers are optional when you're drawing free body diagrams. You can write them off to the side if you prefer. So to figure out the acceleration, I know the mass is 60 kilograms. We calculated that before. And the net force. Okay, so what's the net force? Now, this is a situation where the normal force and the weight, they balance each other, so they don't contribute to the net force. They cancel out. And there's no friction because these are frictionless rollerblades. So the only force that's really acting on the object and changing the motion is this applied force. So you would just say sigma F does equal F for the applied force. So this is a rare case where the applied force is the same as the net force. And so this tells you that the net force is that 200 newtons. And since you know the net force is 200 now, you can divide 200 newtons by 60 kilograms of mass and get your answer. And 200 over 60, that's a number, right? What's 200 over 60? Ooh, 3.3 forever. 3.3 repeating meters per second squared. So that's the acceleration of the rollerblader. So what if there was friction? Well, let's talk about that. Friction is kind of a complicated subject. So what we're going to do is introduce it in its simplest terms, and then later we'll revisit friction and how to calculate it with some fancy equations. But just draw a little box, and let's assume that this box is being pushed maybe by you. You're having a great day and you're pushing the box. So it's got some applied force pushing to the right. And if it's on the ground, then there's going to be some roughness between the box and the ground, and there will be friction that would resist the motion of the box. So we call that friction. Now, you can label friction one of two ways. You can say force sub lowercase f for friction. Or I like to just use a lowercase f for friction. So anytime I use a lowercase f instead of a capital F, I'm saying this is a force of friction. And really the only thing that you need to know right now about friction is that friction is always, not friction, friction is always parallel to the surface. So it actually is a lot like the normal force, except the normal force goes up and is perpendicular. That's why we use the word normal. It means perpendicular. But friction is along the surface. It's parallel to the surface. Okay, let's use it in some problems. You push a 160 Newton or 36 pound box with a force of 120 newtons, which is 27 pounds of force, across a rough floor. So rough floor, whenever you see that, that means there's going to be friction. Friction resists with a force of 80 newtons, which is about 18 pounds of force. Draw a free body diagram, then find the acceleration of the box. Okay, so let's start with the weight and the normal force. The weight of the box is this 160 newtons. The force that you push is 120 newtons, so that's going to go to the right. Now, the box is being supported by a floor, so we would say there is a normal force. And since the box isn't on an elevator, it's not being lifted up or down, then we would say the normal force is equal to the weight. And now I have friction. Now, friction resists. So in this problem, it's assumed that friction would be to the left. And I'm going to label it like that. 80 newtons of force, so I can write 80 newtons like that. Okay, that's our free body diagram. Wonderful job. Now to find the acceleration. Again, to find the acceleration, we'll do the net force divided by the mass. And I can find the mass of the box by taking mg and then dividing by g, right, because that cancels that out. Well, g is 10 meters per second squared, and 160 over 10 gives me 16 kilograms. So that's the mass of the box. The net force. Okay. So the normal force and the weight, again, are balanced in this problem, so they cancel out. And the applied force of 120 is resisted by friction with 80 newtons. So the way that I would find the net force is I would write sigma F equals applied force, it's positive because it's to the right, minus friction, which is negative because friction is to the left. So now I know the net force is 120 newtons minus 80 newtons, which gives me 40 newtons. And I can use this to find the acceleration. 40 newtons divided by the mass of 16 kilograms is a number, gives me 2.5 meters per second squared. And remember that the net force here would be to the right because it's a positive 40 and the applied force is larger than friction. So that means the acceleration is also to the right, which we're choosing to be our positive direction. Good job. Let's do another problem. You stop pushing the box from the last problem. Draw a free body diagram, find the acceleration of the box. Weird. Okay, so hopefully you can still see your problem in your notes. We have a weight of 160, mg equals 160 newtons. And just over here, I'm going to write the mass was 16 kilograms. That's not going to change. The normal force still balances the weight, and so it's also 160 newtons. It's not like the floor fell off in this problem. But now you stop pushing it, so that force is gone. The question is then, what will happen with friction? Well, if you can imagine, the box will slide across the floor and eventually come to a stop. That's because of friction. So the friction force is the same, 80 newtons. And that friction force will constantly be 80 newtons until the box comes to a final stop. So in this problem, to find the acceleration of the box, I'm going to have to look at the net force and the mass. I know the mass is 16 kilograms, but what about the net force? Well, before, the net force was the applied force minus friction. But now, there's no applied force. So all we are left with is friction and this little negative, meaning left. So negative 80 newtons is the net force. And when I divide negative 80 newtons, or the net force, divided by 16, I'm going to get negative 5 meters per second squared. Now what this means is that as the box, if I draw this here, as the box is moving to the right with a velocity, it will have an acceleration backwards of 5, which means that it's slowing down and will eventually come to a stop. Okay, great. Let's do another. You push a 10 kilogram box with a force of 150 newtons so that it moves with a constant velocity. Draw a free body diagram and find the friction acting on the box. Okay, well, let's start with the fact that this is constant velocity. So that tells me there is an acceleration of 0 and a net force of 0. So all of my x and y forces should cancel each other out or be balanced. And that's going to help us draw our free body diagram. So we'll draw a dot to represent the box. And I know that there will be a weight force down, which is mg, and a normal force up. Now, the weight force, if I wanted to calculate it, would just be the mass of 10 kilograms times the acceleration due to gravity, g, which we're using 10 for to make it easy, and that's just 100 newtons. So the weight force is 100 newtons, the normal force is 100 newtons. Okay, so they balance out. Now, the forward force, your push, is going to be forward. Okay, so we'll say it's to the right. And that applied force is going to be 150 newtons. That's your force. Now, in order for the net force acting on the box to be 0, so that there is a constant velocity, then friction has to be in the opposite direction and balance, or be equal to, that applied force. So that's the answer to part B. We know that in order for the net force to be 0, friction has to be 150, or equal to the applied force. And if I was going to write that net force equation out, it'd be F minus friction. So 150 minus 150 equals 0, which is what we are proving. Okay, so the force of friction is 150 newtons. You push a 10 kilogram box with a force of 150 newtons. It speeds up at 1 meter per second squared. Okay, let's draw the free body diagram. You would have, just like what we had before, a weight force, mg, and it's the same box, so 10 times 10, 100 newtons. Normal force up. Those two are equal because the box isn't on an elevator. It's not speeding up or slowing down in a vertical direction. So the normal force is also 100 if we need it. And your forward push of 150 newtons, call that F for applied force, and it speeds up at 1 meter per second squared. Okay, so I know that there's going to be friction to the left, and we're going to need to figure out how much friction there is. But first, let's decide, should my friction force be larger than 150 or smaller than 150? Well, if I'm pushing forward with a force of 150 and the box is speeding up, then that means that there is less friction than my push of 150. So I draw that arrow smaller than 150. Now, I still don't know what it is, but this is totally an acceptable free body diagram because, again, you don't actually have to include the numbers. You can just label the forces, and that's all you really need for a free body diagram. But let's work on finding the force of friction. You know that this object speeds up at 1 meter per second squared. So the acceleration is going to be to the right, or in the same direction as the net force. So we're going to make that a positive 1 meter per second squared. And I can calculate what that net force is by doing mass times acceleration, or 10 kilograms, the mass of the box, times my acceleration of 1 meter per second squared. So 10 newtons. The net force is 10 newtons. Okay, so now to figure out what the force of friction is, I write another equation for net force by looking at the free body diagram. I've got an applied force to the right, so positive F, and then friction to the left, so minus friction. Now, I know that the net force is 10, and the applied force is 150. So now I just have to figure out what will friction need to be so that when I take it away from 150, I'm left with 10. Or we could just, solve this equation algebraically. Add friction to both sides. And then subtract 10. So now I know that friction is 140 newtons. Let's do another slight variation of this problem. You push a 10 kilogram box with a force of 150 newtons. This time it slows down at 1 meter per second squared. Draw a free body diagram. Okay, so weight force, mg, same thing. It's 100 if we need it. Normal force is 100 if we need it. The applied force, 150. Now, the force of friction. Okay, so if the force of friction was less than the applied force, 150, and it sped up because the applied force was bigger, so it sped up, well, now the force of friction has to be bigger than 150 because it's slowing down. So friction is going to be more than the applied force. So that when you're moving, you're pushing the box, but you're actually not pushing more than friction is resisting. So friction is winning, in a sense, and slowing the box down. So your free body diagram would look like this, with the friction force being slightly bigger than the applied force. But we don't know what it is, so let's figure out what the friction force is. We'll start by calculating the net force, mass times acceleration, 10 kilograms times 1 meter per second squared, which is 10 newtons again, just like last time. I'm sorry. Not like last time, because I made a critical mistake. This time it's slowing down, not speeding up. So that means that we're going to use negative 1 meter per second squared. We can assume for these problems the velocities to the right. So negative 1 meter per second squared, which gives me a net force of negative 10. Phew, okay, so that changes the problem slightly. Maybe you already see how. Then to find friction, I write my equation for net force. The applied force to the right, positive, minus friction, because friction is going to the left. And now I have that my net force is negative 10, my applied force is 150, and friction is being subtracted. So we do the same thing. We add friction. So friction minus 10 is 150. We add the friction to both sides. But now I don't actually take away 10 from 150. I add it. So now the friction force is 160 newtons. Let's look at one more type of friction problem. A 20 kilogram box is on the back of a flatbed truck. The truck is speeding up at 5 meters per second squared. Let's assume it's moving to the right. And the box is not sliding. That's important. Is there friction acting on the box? And if so, how much and in what direction? So I'm going to draw the truck and the box on the back of the flatbed truck. The idea is that the box is actually speeding up with the truck and not sliding as it does so. So that means, yes, there is friction between the box and the back of the truck to keep it from sliding. And it is that friction that's actually causing this box to speed up with the truck. Okay, so we'll say the acceleration is to the right, 5 meters per second squared. And so now, when I draw a free body diagram for this object, I'll draw it underneath. I've got the weight down, which 20 kilograms times 10 is 200 newtons. Normal force up, it's not an elevator. So these two are equal. But now I don't have an applied force pushing the box. No. Now, friction is the force that is causing this box to move with the truck. Because think about it, if this surface was made of ice, then the truck would go forward and the box would just stay still. But instead, the box goes forward with the truck. It speeds up with the truck. And that's because it's sort of stuck at the surface. And there's a force of friction that is causing it to speed up with the truck. This is why truck beds are rough, not smooth. Now, To figure out what that force of friction is, I have to realize that the normal force and the weight, they're balanced, and friction is unbalanced. So in this problem, our net force is friction. And it's not negative because it's in the same direction as the acceleration. So to figure out what the net force is, and therefore what the force of friction will be, I just use my mass times acceleration equation. 20 kilograms times 5 meters per second squared. 20 times 5 is a number, right? Yeah, it's 100. It's 100 newtons of force. So that's the net force, and therefore the force of friction. This video is done.